First thing to look at is where there is a big jump in ionization energy, and we can see that that happens after 3 electrons. So 3 electrons are lost, then there is a big jump,
there's going to be about 10 sets of these,
and then it continues to increase. Now, the fact that it jumps after 3 electrons tells us that it's group 3, because that means that the 4th electron is being removed from a lower principal energy level. Now, that means that nitrogen and phosphorus can be dismissed because they are both in group 5, so we're with aluminium and boron. And after that, it's actually a really straightforward means of distinguishing between them, because boron,
grams of molecules, grams of atoms, volumes of molecules, volumes of atoms,
only has 5 electrons, so it couldn't possibly lose 8.
I need to remember that hydrogen is diatomic, so 1 divided by 2.
So we're now looking at which of the following atoms has 2 unpaired electrons in its ground or lowest energy state. Well, let's take a look at them drawn out, and we can see that helium has got 2 in a 1s sublevel actually, beryllium 1s2, 2s2, so they are both paired electrons. When we move on to nitrogen, that has got 3 unpaired electrons when you put those in. Oxygen has 2, so for that reason, the correct answer is
and that is
D.
that 1 mole of any substance occupies a volume of 24 decimeters cubed. Now, with that in mind,
so for this question, you need to have a good working knowledge of ionization energy and the trends, and also the reason for those trends actually. Let's take a look at each of these. We want to know which requires less energy than the first ionization energy of oxygen. We can immediately dismiss B, because second ionization is always higher than first ionization. You're removing the electron from a positive ion, and you've also got a greater attraction on the fewer electrons by the same number of protons. For the rest of it, we can take a look at the graph that you will almost certainly be familiar with if you're revising this now. And we can see when we put this together that nitrogen and fluorine are either side of oxygen in the periodic table, but they're both higher. Oxygen has the dip. We don't actually learn about lithium across the neon, period 2. In the specification, we do sodium to argon, but the pattern is identical, and that is an application that you would be expected to be able to use to get to an answer like this. Now, sulfur, we're actually removing from a higher principal energy level. The electron's being removed from period 3 rather than period 2. So for that reason, the correct answer is A.
If 4 of that is molybdenum, there's only 1 gram of oxygen within there.
So quite fiddly. Let's take a look through what we have here. We've got 5 figures, and we've got magnesium, aluminium, silicon, phosphorus, and sulfur. So it's going across the period in order of atomic number. Now again, if I put out my graph, and we can see the graph that goes there, we've got the general increase with a dip to aluminium and a dip to sulfur. And let's go through the answers and see what we can determine.
Now that's not a whole number ratio.
Well, there are the 5. We can see that aluminium is lower than magnesium. There's an increase to silicon, an increase to phosphorus, but then a dip to sulfur. And let's compare that to the numbers that we have here. Well, A, we've got an increase from the first to the second value. So straight away, we know that cannot be the correct answer. On B, we have a dip, then we have an increase and a dip. So we do see that that follows the pattern exactly. So we can be fairly confident that that is the correct answer. We're going to double check on the remainder of them. Now C, definitely wrong because we've got that increase, but D does follow the pattern. It goes down, then it goes up, then it goes up, then it goes down. However, the drop is far too large. We know that the anomalies in the general trend, when we move to a higher energy P sublevel, or when we have spin-spin repulsion in a P sublevel where 2 electrons are being shared, that the dips are small. They certainly don't go down below any of the other elements than the one that precedes them directly. So D cannot be correct for that reason, so we can be confident that the answer is B.
70 cm cubed remain. On to the next question.
Okay, so this is the second set of atomic structure questions. They are all multiple choice. They're all past paper from AQA A-level chemistry papers. My advice would be to have a look at the question, pause it, try the question, and then follow the video through to double check and see how you've done. Okay, first question coming up.
And then I'm going to put, just as I did with the empirical formula, my M, my MR...
So quite a lot of information to take on here. We've got the idea that helium 2+ particles are being fired at the thin sheet of gold, but only about 1 in 8,000 of the particles are detected at point Q. Now, most will pass straight through. The question really is, why is that the case? Now, as you go through each of the answers, A, B, C and D, there's one that really does stand out. And that's the idea that if very few are reflecting back, it means there's very little to reflect back from. So, correct answer that we're aiming for here is that gold atoms have a small positive nucleus. The vast majority of the helium ions will pass directly through the thin sheet of gold. They won't be deflected at all, but that tiny, tiny number of them will be deflected back when they hit the small positive nucleus.
I've now got a number of moles. I can find the atomic mass of aluminium.
Okay, on this question we're dealing with isotopes. We've got two isotopes of bromine, 79 and 81. And we want to know what statement below is correct. So let's take a look at the ones that we know are not the case. Well, when you consider ionization energy, the change in ionization energy is dependent on the attraction to the nucleus and the shielding by inner electrons. That's no different in the two isotopes, only number of neutrons is different. Atomic radius, similarly, is impacted on by the attraction to the nucleus of the outer electrons and the shielding, and there's no change there. And reactivity is about bromine gaining electrons, and there's absolutely no difference in terms of the attraction, so they are also the same. So that leaves us with the correct answer. And when you add up 3 carbons, 7 hydrogens and a bromine 79, it gives you an MR of 122. When you take 3 carbons, 7 hydrogens and a bromine 81, it will give you a value of 124. And so you do get those 2 molecular ion peaks.
Divided by 1,000, because this is milligrams, and we do our mole calculations with mass in grams.
Okay, a relatively straightforward electron configuration question. So we want to know what the electron configuration is of copper 2+ ions. Now, this is copper itself. It's one of the 2 anomalies, copper and chromium, whereby one of the 4s electrons actually shifts into the 3d, giving us a half-filled 4s and a full 3d. But that's not what the question is. The question wants to know about a copper 2 ion. So we're going to lose 2 electrons. You have to remove 4s before you remove 3d. So it's absolutely vital that you remember that fact. And when you do, you can see that we have lost our 4